Welcome to this video lecture on the Carnot cycle. The Carnot cycle is a type of reversible cycle, and there are many other types of reversible cycles, but the Carnot cycle is a special one. We'll talk about it today. It's often used as a point of comparison for other types of cycles. It's an idealized type of cycle. It's reversible, so it doesn't include real-world effects like friction and viscosity and finite temperature differences for heat transfer and such. But that's okay. Being a reversible cycle, it allows us to have an ideal point of comparison. So you can take real cycles and then compare them against this kind of best case scenario. So being reversible, being idealized is just fine. It's a useful point of comparison. So let's take a look at the screen. If you look at the screen here, you'll see a picture of a rotating detonation engine. So that's what this is. It's a type of engine. It's used to produce power. It's used to produce thrust. It can be used for a jet engine, for example, or a rocket engine. And the reason I'm showing it here is because people are excited about it because it can be up to about 20% more efficient than traditional jet engines or rocket engines. And the efficiency comes about due to the following. If you recall the thermal efficiency for a power cycle, it's going to be the work that you generate from the power cycle divided by the energy put into it via heat transfer. That's like burning the fuel. If you're burning the same fuel, assume that QH is a constant. So if you're going to have higher efficiency, then you're going to have a larger amount of work that you're getting out of it. And the larger amount of work that comes out of it has to do with the type of path that the cycle traces out in a PV plot. And I'm not going to show it here on the screen, but if you go to this video and you look at around the 6.5 minute mark, so the first 6.5 minutes just describes what a rotating detonation engine is, but around 6.5 minutes they start talking a little bit about some of the thermodynamics of it, and they show ultimately a picture of the cycle on a PV plot. And what you find is for this type of rotating detonation engine, you get more work out of the cycle because the area within the PV, the area that the cycle traces out in the PV plot is a larger area, and compared to what's traditionally done for these kinds of engines. So with the larger area, you get more work, and that leads to a greater thermal efficiency. So I thought it was just sort of related to what we're talking about today, since we're talking about thermal efficiencies of reversible cycles and things like that. Okay, so let's start talking about the Carnot cycle in particular. Before we do that, let me just quickly review that, when we talk about these cycles, we're talking about these very general pictures here where we have a hot reservoir, a system, and a cold reservoir. The hot reservoir has an absolute temperature, TH. The cold reservoir has an absolute temperature, TC. This is a power cycle that I'm showing here. I'll just focus on power cycles for today, but everything I talk about here can be also used for refrigeration and heat pump cycles. This circle here is your system. This is where all of the components of your cycle are contained. This could be a piston cylinder. It could have a pump and a turbine and some heat exchangers. All the details are contained in here, as well as the working fluid used in those systems. So could be a gas, could be water, could be some refrigerant. It doesn't really matter, actually. The way that these reversible cycles work, the working fluid doesn't make a difference. What really makes a difference is just the temperature of the hot and cold reservoirs. And as we showed in a previous video lecture, for a reversible power cycle, or just a reversible cycle in general, the thermal efficiency for a power cycle is equal to 1 minus, let me zoom in on this a bit, 1 minus the ratio of the temperatures for the cold reservoir divided by the temperature of the hot reservoir. And again, those are absolute temperatures. So that's what you get for the thermal efficiency for a power cycle. Same sort of thing for coefficient of performance for a refrigeration cycle and heat pump cycle. Those can be written in terms of these absolute temperatures. And one of the things I want to highlight is these performance measures will be identical for any reversible cycle operating between the same two thermal reservoirs. So if you have the same temperatures, TC and TH, for those thermal reservoirs, then you'll get the same performance regardless of what the details of the cycle looks like. We'll come back to that point a little bit later. The other thing is that the efficiency or the performance measures for irreversible cycles will always be less than the performance measures for reversible cycles. We talked about that last time. If you want to calculate the thermal efficiency, for example, for an irreversible cycle, you cannot use the absolute temperatures of the reservoirs. You can only use the absolute temperatures when it's a reversible cycle. If it's irreversible, what you do is you just use the heat transfers. So you can use this expression whether it's reversible or irreversible. So you can always use the heat transfer quantities here, whether it's reversible or irreversible, but you can only use the absolute temperatures if it's reversible. Okay, so just be aware of that. So let me focus specifically on a Carnot cycle. And it's just like I said, one type of internally reversible cycle. There are other types of reversible cycles, like there's an idealized Rankine cycle, for example, an ideal Brayton cycle, for example. So there are other types of reversible cycles, but a Carnot cycle is one that's referred to very frequently. And so I'm going to describe it for you here. I should mention that a Carnot cycle, it can be a power cycle, refrigeration, or heat pump cycle. I'm just going to focus on power cycles just for the sake of time, but everything I describe here holds also for refrigeration and heat pump cycles. Everything that I describe just needs to be run in reverse, basically. Since it's an internally reversible cycle, that means all the process steps are reversible. So that means that everything has to be frictionless, no viscosity in the working fluid. You can't have any energy dissipation there. Everything must be run in a quasi-equilibrium manner, meaning it's always close to equilibrium, so it's operating very slowly, in very small increments. There's no big differences in any of the parameters to cause. Like, for example, when you have a temperature difference, it has to be infinitesimally small temperature difference so that everything's always close to equilibrium. The expansions and compressions occur very slowly, so you'll see we'll have some expansion steps, some compression steps, like with a piston in a cylinder. That has to occur very, very slowly so you don't get any irreversibility due to mixing. And then, as I mentioned before, heat addition and removal, that occurs over negligible temperature difference. Remember, finite temperature differences result in irreversibility, so all the temperatures are all infinitesimally close to one another. So, you need to have all of these things for it to be reversible. It's an idealized, right? So all of these things are idealizations. Of course, real processes have irreversibilities in them. If you were trying to get really high thermal efficiencies by trying to maintain some of these things, it becomes very impractical. For example, heat addition and removal over negligible temperature differences, what that would mean, for example, practically is if you had a heat exchanger, for example, it would have to be some huge heat exchanger so that all along the distance of that heat exchanger, you're always very close in temperature between the working fluid and the thermal reservoirs, right? So it's just not practical. You just can't do it. So it's an idealization. All real processes will have some irreversibility to them. Now let me describe the steps in a Carnot power cycle. Again, I'm just going to focus on a power cycle. You can do the same idea for refrigeration and heat pump cycles. You just run these things in reverse. So for the Carnot power cycle, the power cycle, there are 4 processes. From 1 to 2, it's an isothermal expansion at the hot reservoir temperature, TH. So I've illustrated that below here for piston cylinder arrangement. So here's our hot reservoir with temperature TH, that's an absolute temperature. We're getting some heat transfer into our working fluid here, and that's causing some expansion. We're doing some PDV work on this piston, and it's expanding. So on a PV plot shown right here, I'm showing this PV plot specifically for a substance that's a vapor. So if you remember, let me just kind of sketch this out for showing a substance where we have a vapor dome, and let me show an isotherm. So there's a T equals a constant. What we're doing is we're operating out in the superheated vapor region, so like out in here. Right, it stays a vapor, so we're out in this region. So you can see your isotherms are going from upper left to lower right. So you can see an isotherm for the TH, hot reservoir temperature. There's the TC isotherm there for the cold reservoir temperature. So going from 1 to 2, that isothermal expansion, we're staying at the same temperature, from 1 to 2, and it's an expansion, so the specific volume is increasing. We're going from left, well, you can see we're going from left to right here. The specific volume is increasing. So that's our isothermal expansion from 1 to 2. 2 to 3 is adiabatic expansion to the cold reservoir temperature. So here's from 2 to 3, it's expansion again, so 2 is to the left of 3, so we're expanding, specific volume is increasing, and we're going from the hot reservoir isotherm to the cold reservoir isotherm. And graphically, that's shown here. You can see there's no heat transfer because it's adiabatic. We still have an expansion, so we're doing some PDV work on the surroundings. So that's, again, it's expanding. So that's that step. 3 to 4 is an isothermal compression at the cold reservoir temperature. So here's 3 to 4 on that cold reservoir isotherm. It's a compression, so you can see we're moving from right to left on the specific volume axis. Graphically down here for piston cylinder arrangement, you can see that occurring. Here's our compression, so we're doing work on the working fluid. There's some heat transfer out into the cold reservoir. And then 4 to 1 is an adiabatic compression back to the hot reservoir temperature. So 4 to 1 is here. It's occurring adiabatically, shown down here. There's no heat transfer occurring. It's a compression, so we're moving from right to left on the specific volume axis, and we're doing work on the working fluid. And then we've closed out the cycle. So that's what our Carnot cycle looks like on a PV plot for a substance that remains a vapor. Now, we could also do a Carnot power cycle for a working fluid that is a saturated liquid vapor mixture. So I've shown that here, one with a bunch of different components. So it's just I just want to show that you can do Carnot cycles for different scenarios here. The system can change. Right? So here, for example, is one type of system, piston cylinder. Here's another type of system. And these systems I'm talking about are this part. So it could be a piston cylinder, it could be one with a bunch of components. Again, the details don't matter. The thermal efficiency will be given by these temperatures here. Okay, so anyway, let me just show you what it looks like for one with saturated liquid vapor mixture for your working fluid and having different components. So from 1 to 2, okay, so here's our PV plot and our vapor dome. There's our hot reservoir isotherm, our cold reservoir isotherm. From 1 to 2, we're doing our isothermal expansion. So isothermal, because you see that we're operating on the same isotherm, and it's an expansion, so we're going from left to right on the specific volume plot. That's occurring on this plot. The points 1 and 2 are right here. So point 1 is here, point 2 is here. So that's our heat exchanger, where we're putting some energy into our working fluid as we go across. The pressure remains constant during that process. And then from 2 to 3, that's our adiabatic expansion. Again, expansion 2 is to the left of 3 here on the specific volume plot. And we're going from the hot isotherm to the cold isotherm. That's occurring through the turbine. So point 3 is here. We're getting some work out of it there through our turbine. And then 3 to 4 is across this other heat exchanger where we're removing some energy into the cold reservoir. So that's occurring on that cold isotherm. And then 4 to 1 is our adiabatic compression to get us back to the hot isotherm, and that occurs on our pump. So it's compressing the fluid to get us back to state 1 to complete our cycle. So that's what a Carnot cycle looks like for a saturated liquid vapor mixture situation. And here's a corresponding picture to go along with it. Again, the thermal efficiency for this Carnot cycle will be the reversible thermal efficiency, so it means it'll be 1 minus Tc over Th. It only depends on what the temperatures are for our hot and cold reservoirs. Okay, so, and then that will be the maximum thermal efficiency you can have for a power cycle between those same two thermal reservoirs. Nothing's going to get any better than that. Now, I mentioned that there are other types of reversible power cycles, so let me show you an example of one that we'll talk about later in the course, but I'll just give you a preview. And that one I'm going to talk about is a Rankine cycle, so let me just sketch it here on a PV plot. fix that a little bit. Okay, so that one, let me sketch out what a typical cycle would look like for a Rankine cycle here. Let me sketch it out and then I'll talk about it in a moment. Okay, so the points here, so this is an ideal Rankine cycle. This one is the Carnot cycle. And again, you can have a reversible Rankine cycle. It's just it's a different set of paths. Okay, it's a different set of processes, but it can still be reversible. And on this PV plot, what we have here is point 1 is right there, point 2 is here. So this is going through the heat exchanger. It's a constant pressure process. We're adding our energy in, the Q in comes in there. 2 to 3 is right here. It's going through the turbine. 3 to 4 is here. That's the other heat exchanger. And then 4 to 1, like the pump, is right here, where the pressure, you can see the pressure is increasing. 2 to 3, that's the turbine. You can see the pressure is decreasing. And what I want to do is just kind of sketch out what the isotherms look like here. You can see there's one isotherm that goes like this. Another isotherm would go here. So this might be the TC one. You can see during the heat exchanger process down here from 3 to 4, that occurs, the way I've drawn it here at least, that occurs at a constant temperature. But the heating process here from 1 to 2, you can see that the temperature, the isotherms are different. Right? So you can see, for example, I'm crossing several isotherms. Right? So I have several different isotherms as I'm adding the heat from 1 to 2. Right? There's a little cooler temperature, gets a little warmer, here it's a little warmer. So the hot reservoir for the Rankine cycle, the way I've drawn it on this particular diagram, the temperature is changing. Right? It's just not, it's not a constant temperature. It's not at a constant TH like I have up here, but the isotherms are changing as I go from 1 to 2, so that the hot reservoir temperature is not a constant, but it varies. And so what ends up happening is for an ideal Rankine cycle, the TH, when I go to this expression to calculate the thermal efficiency, the TH is not necessarily the same TH that you would have here in the Carnot cycle, where it's just a constant TH. Here the TH varies. And so what you'd find is that in the ideal Rankine cycle, the average TH that you have is actually a little less than what you'd have for the Carnot cycle. And so the point I'm trying to make here is that even if you have an ideal Rankine cycle, because the hot thermal reservoir does not stay at a constant temperature, but its average temperature is typically a bit lower than what you'd have for the Carnot cycle, the reversible Rankine cycle will have a smaller thermal efficiency than the Carnot cycle. So even though they're both reversible cycles, the Carnot cycle will have the highest efficiency because its TH is higher than the effective TH in a Rankine cycle. So I want to make that clear that even though they're both reversible cycles, the Carnot cycle will have a higher thermal efficiency only because its TH is higher. It's not, the thermal reservoirs are not the same between the ideal Rankine cycle and the Carnot cycle. Okay, so if you had the same reservoirs, if it was the same TC and the same TH, then they would have the same thermal efficiency, guaranteed. But even though they're reversible, the TH for the ideal Rankine cycle, as I've drawn it here, is different. So it will have a smaller thermal efficiency because its average TH temperature is smaller. So the Carnot cycle, the reason I'm telling you all that is we're going to come back to this point a little bit later in the course, so I'm just giving you an advanced preview. But the reason I'm telling you mainly is because the Carnot cycle is really, out of all of these different reversible cycles, it's really the best reversible cycle. When you're operating between a TH and a TC, the Carnot cycle will have the best, well, it'll have the best thermal performance because its average TH will be higher than the average TH for other types of cycles, for example. Okay, I know that's a little confusing, but we're going to come back to it later in the course. But anyway, this is why Carnot cycles are often cited, is because they're really an ideal, very simple kind of cycle, and of course, being reversible, it's going to have the highest thermal performance when you're operating between two given thermal reservoirs. Okay, I think that's everything I want to talk about in this lecture, so we're going to go ahead and end it there.